Alright, so moving on to the conservation of angular momentum equations. This is quite a long one, so again, please try to stay with me as best as you can. I'm going to try and explain this as thoroughly as possible because this is important stuff. And I think it's worthwhile going through this in a lot of detail. So to start this derivation off, we actually return to our equation star from our derivation of the conservation of linear momentum equations. You recall star was this equation here. And we start by using this equation, and all I've done is just pushed one of these derivatives inside of the integral. The rest of it stays the same. Okay, so one of those derivatives goes inside the integral, the rest of it stays the same. And we recall how we express angular momentum, which we define as L, as a position vector crossed with the linear momentum, which is mass times the velocity vector. So if we consider our position vector again, r bar dash, so remember r bar dash was the vector relating our chunk of aircraft that we're describing with mass dm, surface or shape d capital S, and volume dv to the origin of the Earth-based inertial reference system, which, as we said in the previous video, is the sum of the vector describing the distance between our little chunk of aircraft to the aircraft center of gravity, which is also the origin of the body axis system, plus this vector here, r bar p dash, which relates the aircraft center of gravity to the origin of the Earth-based inertial frame. So this vector is the sum of these two vectors, as we've just described, and therefore we can convert our equations for the linear momentum, the conservation thereof, into the angular momentum equations by taking the cross product of r, which is our position vector, and the linear momentum, which we've just found, right? So this part here describes the conservation of linear momentum equations that we've just found. We just take the cross product of those equations with this position vector r, or r bar dash in our case. So we take this equation here, take the cross product of each term with r bar dash. That's exactly what I've done there. And then using the fact that r bar is the sum of these two vectors, we can rewrite this equation in this slightly more lengthy form where we just replace r bar dash with the sum of r bar dash sub p plus r bar. And for convenience, for when returning to this, I've just called this the left-hand side and this the right-hand side. All right, so the first thing I've done is gone ahead and expanded it out I've expanded out the right hand side by taking these cross products from inside the brackets to get this. So I've got r bar dash sub p crossed with the first part of this derivative plus r bar dash sub p crossed with the second part of this derivative plus the r bar terms, so I get 4 terms here on the right hand side, and I'm calling those numerals because this is going to get complex in a moment. I'm calling these numerals 1 through 4, okay? And obviously the expansion of this equals the left hand side, which is just what I've written here for mathematical correctness. I've also expanded out the left hand side, so again I get 4 terms based on expanding out this bracket here, crossing it with the g, the gravity vector, and then also expanding out these terms here. I've actually left the brackets including the aerodynamic and thrust forces in there. So I've just got 4 terms on both sides. Left hand side equals the right hand side, and what we do is deal with each of these 8 terms now individually. So here we go then, starting with term number 1, which was on the right hand side, remember this one. And what we can do is, the first step is to use the product rule to expand out this term here. So we get the derivative of one thing multiplied by the other plus the other thing multiplied by the derivative of the other, which is these 2 terms here. And remember from linear algebra that the cross product of 2 vectors which are the same is 0, so this whole term here goes to 0, so we're just left with this term. Also recall how we describe mass, and also remember that our position vector doesn't depend on volume or mass, right? That's fairly intuitive. So we can rewrite this as, if we take the r bar p dash outside of the integral, we're left with mass multiplied by this derivative. Or if we use our conservation of linear momentum equations, we've seen this term here before, right? That was just the right hand side. Let me find my other notes. That was just the right hand side of our linear momentum equations. These terms here, right? So we can rewrite this where we replace the derivative of Vp bar with respect to t as these terms. But then we make a little bit of a trick, right, and rewrite this thing again in integral form. So we split those terms up again to get this. And we see that what we're left with, these 2 terms, is in fact the terms numbers 5 and 7 from the left hand side. 5 and 7. So what we've just shown is that 1 will eventually cancel with 5 and 7. So let's move on to term number 2. So term number 2, we do exactly the same thing as we did for number 1. We split it up using the product rule to get these 2 terms, but now we don't have the cross product of the same 2 vectors, so we actually have to deal with both of these terms separately. We can take out our r bar dash sub p vector though, because that doesn't depend on volume or mass from the integrals. So that's what I've done here, is I've taken those terms out of the integral both times. And then what we can see here is that we're actually left with these 2 integrals which look the same. And remember from our derivation of the conservation of linear momentum equations that if r bar, so this is the vector relating our chunk of aircraft to the center of gravity position. So if the aircraft is in trim, then the net moments about that point are 0. So that's we're going to assume that this is equal to 0, based on the same assumptions that we use for the derivation of the linear momentum equations, and therefore term number 2 is 0. So you can see how we're actually reducing down this huge thing to get to something a bit more manageable. So far we have that 1 is going to cancel with 5 and 7, 2 is going to be 0. We'll now move on to term number 3. Term number 3 then, so we do exactly the same thing again. By the product rule we can split up these terms here into 2 separate integrals, and then we use a little bit of linear algebra again, so some identities about the cross product. The cross product of 2 vectors A and B is the negative of B cross A, so that we're able to rewrite this thing with this term appearing first in the cross product and a negative sign, and then this thing here where this term appears first in the cross product with a negative sign. And then again, because r bar p dash doesn't depend on the volume or mass, of the aircraft, we can take it outside of the integral to find this here again. So these are our moment arms multiplied by the mass. So if R bar describes the position of our chunk of aircraft with respect to the aircraft center of gravity, then the net moments are 0. So these terms again are 0, like we showed for term number 2. So again, we see that term number 3 is 0. So again, we're reducing this system down a lot. The 6th term, which is on the left-hand side, this one, again, we can use that identity, this one here, to put the the G gravity vector first in the cross product, include the negative sign, then take the gravity vector outside of the integral, and we're left again with this term, which we keep saying is going to be 0. So another term reduces to 0. So just to summarize where we're at the moment, this was our huge equation here, which we labeled terms 1 through to 8. Well, we've shown that 1 is going to cancel with 5 and 7, and terms 2, 3, and 6 are all 0. So we're just left with number 4 on the left-hand side is equal to number 8 on the right-hand side. So if number 4 equals number 8, I've just gone ahead and rewrote that. What we have on the right-hand side is this R bar, which is our moment arm for these aerodynamic and thrust forces, right? So the moment arm multiplied by the force is just the moment, right? Force times distance. So we can rewrite this as number 4, right, which was this thing on the left-hand side, is equal to the moments associated with the aerodynamic forces and the thrust forces. Then again, this side can be split up using the product rule. Again, we have this cropping up here, which is the cross product of 2 of the same vectors, that's 0. So we're just actually left with one integral on the left-hand side, which is the cross product of R bar with the second derivative of R bar with respect to t, and then these 2 moments on the right-hand side. So this is the conservation of angular momentum with respect to the Earth axis system. So as we did for the conservation of linear momentum equations, the next step is to rewrite this with respect to the body axis system. So I hope you're all still with me. I haven't all fallen asleep yet. I told you this was going to be quite dry. But let's go ahead and try to formulate the conservation of angular momentum equations with respect to the body axis system now. So recall in our derivation of the conservation of linear momentum equations, we wrote the derivative of R bar with respect to t as the partial derivative plus this term here, which describes the rotation of our vectors field. And we introduce this notation dot to represent the partial derivative of this term with respect to t. So if this is the first derivative, then the second derivative is just d by dt of this, right? So this thing here I'm calling double cross or whatever. I'm going to refer to that again in a moment, so just keep that in the back of your minds. So the conservation of angular momentum equations, this one here, now becomes this thing. So I've just replaced R bar, right, in this term here with this definition here. So I've got the second derivative of R bar with respect to t, which is what I've replaced with this, and then I've just got R bar from here. So we now do a little bit more algebraic trickery and call this thing here, inside this bracket here, C bar. So what we are able to do is say what the derivative of C bar with respect to t is using this same definition as up here, right? So if we just replace R bar with C bar, then the derivative of c bar with respect to t is the partial derivative of c bar with respect to t plus the cross product of omega with c bar, which is what I've got there. So basically what I'm doing is this in a progression form, right? So if this is the partial derivative of if this is the derivative of c bar with respect to t, then I can replace what c bar is in this expression with this, right? So this, if I take this and replace c bar with the definition of c bar, which is this, I get this equation. Then on this equation I can apply, on this term here I can apply the product rule again, right? So dr bar dot with respect to t is r bar double dot, then I get w cross r terms, so I've taken the derivative of this with respect to t multiplied by this, and then I do the derivative of this with respect to t multiplied by this, that's the product rule. And then I've just split up these terms here, so I've multiplied those brackets out. Then, so I've collected these two terms together to get two of these cross products. And then we have to apply some more of our assumptions to cancel this down a little bit. Sorry, finger in the video there. So we've got a rigid body assumption, right? So we're assuming that our aircraft doesn't flex or bend. So that means the distance between any 2 points on the aircraft never changes. So the position of any 2 points with respect to time, so the derivatives of r with respect to t are going to be 0. So that term and that term both are 0, and therefore we can rewrite our integral from up here like this. So these terms go into here now. So now we can use yet another linear algebra identity, this time to do with the cross products and how to convert them into dot products. Which means we can rewrite some of these terms. So this term here, the cross product of the cross product, as something multiplied by a dot product, subtract something multiplied by another dot product, right? So that's what I've done here, expanded that out. And then, so what we get when we multiply this out with this cross product of r bar at the front here is another cross product of a cross product. We apply this thing again to get these two terms, and then this one, but this one is 0 because we've said this previously that the cross product of two of the same vectors is 0. So we've applied that identity twice to get 3 more terms equal to these moments. And I've called those terms numbers 1, 2, and 3 to be different from our Roman numerals that we used earlier on. So again, if we go ahead and define our components of these vectors, r bar, omega bar, and omega bar dot, which is the derivative of omega, as x, y's, and z's, and p, q's, and r's. So remember, these are with respect to the body axis system now, and these are rotations with respect to the body axis system. Then we can just calculate our little individual dot products from in here. So r dotted with r is just the dot product of this with itself, so x squared plus y squared plus c squared. R bar dotted with omega bar dot is this, and so on. And what that's going to allow us to do is rewrite this equation using all of those dot products that we've just calculated there. So remember, we labeled these terms here individually 1, 2, and 3. Well, 1 becomes this thing where we replace the dot products that we've just calculated into here. Number 2 becomes this, where we've replaced those dot products into here. And what we see is that because number 2 has a negative sign, right, that when we start to expand out these brackets, we get a lot of terms which cancel between 1 and 2, right? So for example, we've got p dot multiplied by x squared here. That's going to cancel with p dot multiplied by x squared, right? So again, negative sign here in term number 2 means that a lot of these terms cancel in this equation here. So, bearing that in mind, and all of these terms which cancel, we sum these terms numbers 1 and 2 from this equation to get this horrible looking thing here, where I've grouped together I bars, J bars and K bars. Now, the last little bit that we need to discuss about this horrible looking equation here is what these terms actually mean. Well, it turns out that these are the definitions of moments or products of inertia. So for example, the definition of the moment of inertia of the aircraft along the x-axis passing through the aircraft's centre of gravity, so remember that's the origin of our body axis system, is given by this. So if we have n discrete point masses for our little individual chunks of aircraft, then the moment of inertia is the sum of those distances in the y direction and z directions multiplied by those individual point masses. So this is a moment of inertia of the aircraft along the x-axis, y-axis and z-axis, and then all of these terms are products of inertia, which are moments of inertia about multiple axes, right? So for example, the product of inertia about the x and y-axis of a discrete point mass m is just given by this equation here, which is this. So products of inertia here, moments of inertia here. So now what we can actually go ahead and do is rewrite this horrible looking thing here in a much more neater form by using the definitions of the moments of inertia and products of inertia. So all of this mess here just becomes this. So remember that is just terms numbers 1 and 2 added together from this equation over here. So we're still left to deal with term number 3. So term number 3 is going to actually be a little bit more complicated than 1 and 2 just because we've got this cross product here. So rewriting out term number 3 in its full form, we're going to deal with the cross product first. So again, we take the determinant of x, y and z and p, q and r to get this, and therefore if we write this equation out, separating out I hats, j hats and k hats, when we replace this back in here, we get these 3 terms here. So I hats multiplied by the integral of this, j hats multiplied by the integral of this, k hats blah, blah, blah. And then again, we end up with 3 other terms of this equation, which I've denoted dash, double dash and triple dash, which we're going to go ahead and deal with separately again. So hopefully you're following this and how we're going to piece it all together at the end. So on to page number 11. First term we're going to deal with from up here is going to be single dash. We're going to multiply all of these terms out in these brackets to get this horrible looking thing, and then what we get here is a lot more of those definitions of moments and products of inertia. So recall the integral over v of something with an xy term in it. Where's it gone? It's up here, look. So again, we're going to use these definitions to reduce this horrible looking thing down to this, and then we're going to do a little bit of an algebraic trick on this term here. So the integral over v of this, we can take the q and r out, the components of the angular velocity vector, so we're left with this, And then again, we're going to just use a little bit of an algebraic trick. We're going to add the other component in the other axis, so x squared, so that we can write this as two separate integrals. So if we add x squared here and then take it away here, right? So we've just basically expanded this out using a dummy variable. We end up with two things which we've seen before, right? These integrals over v of y squared plus x squared and integral over v of z squared plus x squared resemble these things. So these are more moments of inertia. So what we actually get here is QR multiplied by the difference between these two moments of inertia, and then we can rewrite this I bar equation just plugging this back into here, which is what I've done here. I can do exactly the same thing for term double star, which is this one. Exactly the same. Sorry about the squeaky chair. Expand everything out, write everything in terms of products of inertia where we can. Do the same algebraic trick on this term here where we add and then subtract the dummy variable y squared to get these moments of inertia and rewrite the j hat term. So finally, looking at the triple dash term, this one, again we multiply everything out, write in terms of products of inertia, use the algebraic trick on this final term here, this time with the dummy variable z squared, add it, then subtract it back off to get this. And finally, our equations, so these ones we've all written out here. We've calculated all of those, written them out in terms of moments and products of inertia. But those ones, remember, all are inside this third term of this equation here, which was on page number 8, right? And we already calculated 1 plus 2, right? That was this thing, that was this huge thing here, which became this. So to complete this equation here on page 8, we take 1 and 2 that we've also already calculated, and 3, which we split up into dash, double dash, and triple dash, right? Which is that plus dash, double dash, and triple dash to get this mess here. Okay, so in order to move on from this mess, we need to consider one of our other assumptions about our aircraft. So for most aircraft, in most situations, there are some exceptions as we've discussed previously. We're going to assume that the mass distribution of our aircraft is symmetric in the XY plane and the YZ plane, but is not symmetric in the XZ plane. So if I get Dusty, so Dusty is typical of a lot of aircraft. He's symmetrical in that plane, he's symmetrical in that plane, but he's not symmetrical in that plane, right? So that's the assumption that we're going to use to reduce this horrible mess down. So if our aircraft is symmetric in the XY plane and XZ plane, then our moments of inertia about those axes is going to be 0, but we can't assume that the aircraft is symmetrical in this plane, so we're going to leave these terms inside of our equation. So all of our products of inertia, x, y, and y, z, in this equation here, we're going to cancel, but we're going to leave all of the products of inertia, x, z. So actually, this huge thing here just reduces to this, again, where I've just left it in component form, I bars, j bars, and k bars. We can also write down our moment, aerodynamic moments and thrust moments in component form, L's, M's and N's, which allows us to finally write our conservation of angular momentum equations with respect to the body axis system as this thing. So I've also labelled everything that's going on in these equations here. Let's start with the more simple terms. So I've left this in component form, right? So this is grouping all of the I hats, this is called the I bars, this is grouping all of the J bars, this is grouping all the K bars. So this equation here relates to our roll moment equation. So roll because it's about the x-axis, so remember the x-axis is out the nose, so if we're rotating about the x-axis, that's roll. This is our pitch moment equation because it's about the y-axis, so remember the y-axis is out, positive out of the right wing, so if we're rotating about the y-axis it's pitch. And this is our yaw moment equation because it's about the z-axis, which is downwards. So if we're rotating about the z-axis, we get yaw. So, for example, these terms on the right-hand side, so this is a roll moment, this is roll moment because it's in the roll moment equation. This is roll moment due to the aerodynamic forces. This is pitch moment because it's a pitch moment equation about the y-axis, so this is pitch moment due to thrust forces and so on. So what do we have on the left hand side? Well, we have some angular acceleration terms. So these are our angular, so the angular velocity vector is p, q and r. We've got dots here which correspond to the derivatives of those velocities with respect to time, so these are actually accelerations. We also have some inertial coupling terms, so remember we left in all of the moments of inertia with respect to the x and z axis because that's the only one that's not symmetric. And these terms here are what are referred to as gyroscopic precession terms. So these describe how if we have rates in two axes, that they actually couple into the third axis. So you'll see here that in the roll moment equation, which is about the x-axis, we have terms here in the z and y and so on. So we got there in the end. Hopefully you followed me all the way through that. We have now the conservation of linear momentum equations and a system of conservation of angular momentum equations. They must be considered together as a system of 6 first-order ordinary differential equations because, for example, the solution for the velocity vector, omega, p, q and r, appears in both sets of equations, right? So if we solve one, they have to also be the solution of the other. So there we go. Conservation of linear and angular momentum equations.